Why do these different ways that we've looked at separate light into its colors? The reason is because red, orange, yellow, green, blue, indigo, and violet light differs according to wavelength, and so they are bent differently as they travel through something like water or glass. What do I mean by this? Let's go back to our simulation. Notice here that it says for the red light 650 nm. That means 650 nanometers. What does that mean, and how does that change as we change the color of light? Take a look. So now I'm going to change the color of light to yellow, and that changes the wavelength here to 582 nanometers. In other words, it makes the wavelength shorter. Let's change the color of light to green. There are a number of shades of green, but let's stop here. 539 nanometers, even shorter. And then we change it even shorter. There we've got blue light, make the wavelength even shorter. We have a darker blue light and even shorter. Now we're getting into the indigo and the violet. There we have violet light, 380 nanometers. Let's make this a wave. You know, like you get a wave in the sea, you get high points and low points. And that is kind of what we're seeing here. It's a simplification, of course, but we can think of it like that. So we could think of the dark lines here as the low points in the wave and the lighter lines as the high points in the wave. So notice how this changes as we change the color of light. So here we have the violet light, and now we're going to make it, now it's more indigo. So we are increasing the wavelength. Now we've got blue light. What do you see is different between this blue light and the purple we had just now? Let's make it lighter blue. Can you see that the wavelength is getting longer? The distance between the light sections is getting further apart. This is green light now, yellow light. You see that those distances are even getting further and further. It's like the waves are getting longer and longer. That's what this number here means. It's the wavelength, it's the distance between two crests, two high points in the wave, two bright lines here in this wave. And so when this number is high, as you can see in the simulation, the distance between the bright parts is longer. So that helps us understand what color is. Of course, we know what color looks like to our brains, but why does it look like that? The reason why we see different colors is because the light of different colors has different wavelengths. So here is red light, and the distance between the bright parts is longer, which we can think of like the distance between two crests, two high points in the wave being longer. Actually, light is not this simple, but let's use this to understand for the moment. Meanwhile, here we have violet light, and you can see here in the radiation diagram how the bright lines are closer together, which is like the wave tops, the crests of the waves being closer together. The wave is shorter, and that's why the number here is smaller than the number here. The wavelength of this violet light is 400 nanometers. The wavelength of this red light is 700 nanometers. So red light has a long wavelength. Violet light has a short wavelength. Nanometers means billionth of a meter. So the distance between two crests that are next to one another for red light is 700 billionths of a meter, which is very, very short. But that is longer than the distance between two crests in violet light, which is only 400 billionths of a meter. So if we come back to our spectrum, the reason why our eyes see different colors is because the different colors have different wavelengths. Red light has the longest wavelength of those colors we can see. Violet light has the shortest wavelength of those colors we can see. And these other colors have in-between wavelengths. And this is also the reason why the colors spread out. Because when light is bent, for example, by a prism or by a CD or by water, red light with its long wavelength is not bent so much, whereas violet light with its short wavelength is bent a lot. The short wavelength causes it to get bent a lot, and so the colors are bent differently. And so because they bend differently, they spread apart from one another. They don't stay together. when they're just traveling through air or just traveling through space, there's nothing there to bend the light. So the different colors don't get bent differently to separate them. They all stay together. But once they reach something which can bend the light, then the colors, because they have different wavelengths, get bent to different degrees. And that's why they get spread out apart from one another. Now there's one last thing we must understand. We've spoken here about wavelength, that red light has a long wavelength and violet has a short wavelength. But now let's look at it in a different way. So let's go back to our simulation, and this time I want you to concentrate not on how close the bright lines are to one another, but rather on how many bright lines you see passing a point in a second. So you can see these bright lines, bright and dark lines, moving away from the luminous object. And if you just keep your eye at one point, what do you notice as we change the color of light? So if you look here at this blue light, if you see how many of those lines are passing a point in a second, is it many or is it few? Now let's increase the wavelength all the way to red light and compare what you see. Can you see with the red light, fewer of those bright lights pass a point every second? But with the violet light, many of those bright lines pass a point in a second. And we call this frequency. So the red light is long. It has a long wavelength. The bright lines are far apart, but it has a low frequency. Only a few bright parts pass a point per second. Whenever wavelength is long, frequency is less for light. Whereas with the violet light, the wavelength is short. The distance between the bright sections is short, but the frequency is high. Many of those bright lines pass a point per second. Whenever light has a short wavelength, it has a high frequency. You can see the two go against one another. Long wavelength with low frequency, short wavelength with high frequency. So let's recap. White light can be dispersed. That means it can be split into its colors. The colors that are inside white light are Roigbiv, red, orange, yellow, green, blue, indigo, violet. Roigbiv. These make up the spectrum of visible light. How can white light be split into its colors? It can be split, it can be dispersed by anything that will bend the light enough that you can notice the spectrum clearly. For example, you can use a triangular prism or water, as happens with raindrops in the sky when we see a rainbow. And what these things do is that they cause each of the colors of light to be bent to a different amount, pulling the colors apart from one another. And the reason why they bend to different amounts is because the different colors have different wavelengths and frequencies. Red light has the longest wavelength and the lowest frequency of the colors of the visible spectrum. Violet light has the shortest wavelength and the highest frequency of the colors of the visible spectrum.